So today we are going to discuss about impulse and the linear momentum. So in the last lesson we discussed about the Newton's second law. So what is Newton's second law? Newton's second law is F is equal to delta P divided by delta T. Momentum difference divided by time. So P means momentum, delta P means momentum difference. So this is nothing but P final minus P initial. Momentum difference is initial momentum difference between initial and the final. And this is delta T here. Now, what is P final? That is going to be MV final minus MV initial divided by delta T. Right? Delta T. Now, you can cross multiply now. So when you cross multiply, you get F times delta T is equal to MVF final momentum minus initial momentum. So we have to understand this is nothing but P final minus P initial. So in short, you can say F delta T is equal to delta P. So that you can easily obtain from here. Now, this F times delta T, this term is defined as I, which is impulse. Impulse. So in summary, we have to understand impulse is F times delta T, and impulse can be written as linear momentum change. You can see that from here. So momentum change is the impulse. Right? So you can have a question in this way. So there is one object here. Right? There is another object here. Suppose this is M1, this is M2. Initially, the speed is 0 here. Initially, this one has U1, this is U2. Then definitely they collide, right? So definitely they collide. So when they collide, I'm just consider M1. M1 is going to have a velocity V1, and V1 is obviously less than U1. Okay. So I'm not going to consider M2. M2 is there. M2 is moving, right? We will just consider M1. So now if you just consider M1, you will see the velocity difference. What is the velocity difference? If you just look at M1, velocity difference would be U1 is greater minus V1. That is the velocity or the speed difference in this case. So if you multiply that with M1, that is nothing but momentum difference of M1 object. Momentum difference of M1. This should be very clear. The same calculation you can do with M2. Okay. So now obviously this is a collision. Without a collision, U1 is not going to be V1 because we consider there are no resistance, there are no friction, right? So under those conditions, there shouldn't be any speed difference unless there is a collision. So indeed there is a collision. So because of this collision, there is a speed difference. Then there is a momentum difference. That's the story. Now you understand when they collide, that means there is an exchange in support force, right? So when you touch someone, you can see that you are literally pushing or pulling. Support force. So at the collision, you will see the support force. Now, if that support force is acting on this for a very small time, because the collisions are happening in a instantaneously, you can say. So in this case, we can easily find delta p. So you can easily calculate impulse. You can easily calculate impulse I. That is nothing but this delta p, right? So when you know the mass and the velocities or the speeds, you can easily calculate I. So once you calculate I, right, so you know the relation I is equal to F times delta t. F times delta t. What is this delta t? Delta t means collision time, right? Delta t means collision time. So F means the force exchanged between those two objects, right? So we can say average force act between those two, right? I would say average force. So if you know the time, collision time, if the collision time is given to you, right, in some questions they will give you the collision time, so you can find the force, that to be impulse divided by delta t. Okay, so this construction you must master. Okay, so this is the definition of impulse. So linear momentum we discussed last week as well, that is mv, right? Now next we are going to discuss about linear momentum conservation. That's the next topic. Linear momentum conservation. Okay, so linear momentum conservation, again, F times delta t is equal to delta p, or mvf minus mvi, or p final minus p initial. So when the applied force or the external force is equal to 0, according to the formulation, you can see p final is equal to p initial. So this is called linear momentum conservation. So in absence of an external field, external force, you can apply linear momentum conservation. So now we will discuss an example. So think about this system. So you have m1 here, the speed is u1. You have m2 here, the initial speed is u2. u1 is greater than u2. So obviously there will be a collision then. So when the collision is happening, okay, so when the collision is happening, it looks like this. So this is happening very quickly. So we would say delta t is very small, right? So delta t is very small. So after situation looks like this. m1, m2. Suppose this one is v1. The speed of this one is v2, and v2 is greater than v1, right? So this is before situation, and this is after situation. So if you calculate the momentum before momentum, so I would say momentum initial of the system, you should get m1 u1 plus m2 u2, right? Then p final for the system means for this whole thing, p final for the system, and that would be m1 v1 plus m2 v2. Okay, so if you think about the whole system, there are no any applied external forces, they are just moving. Collision is happening. Now if you just think about the collision, there will be two forces acting on this, action reactions. You can see support force due to this touch, action reaction. So if you think about this system, you can consider those two forces to be internal forces. Right? So no external forces. So they internally cancel each other. So this is a system where we cannot find an external force, external contribution. So we can definitely use linear momentum conservation. So you can say that using linear momentum conservation, you can say that P final is equal to P initial. So in that case, you can say M1U1 plus M2U2 is equal to M1V1 plus M2V2. So this is the relation we get using linear momentum conservation.